Wolfgang Sergel. And then he went on to do a postdoc in Oxford at the MPI in Bonn, and then moved via South Korea. So is it Kyoto? Sorry, Kyoto, yes. I try to remember from our business. Maybe I had a class for one. Yeah, so Kyoto, and then he moved on to Sydney. He works on representation theory, and he had a very interesting paper together with DeepMind on how this type of interaction between, let's say, machine learning techniques and mathematics could go. And lastly, François Charton, he studied at the École Polytechnique. Then again, he worked with many different companies. He founded his own company. I won't name all of them, but now he's at Meta AI and working on stuff. Well, he's a researcher at Meta AI and working on questions on how AI and mathematics or general AI and science can play together. So yeah, I'm very happy to have this panel here. Now everybody gets, as I said, roughly 3 minutes to give a few thoughts on the topic of the panel, mathematics.
So when I told my friend, the mathematician Peter Doyle, who teaches at Dartmouth, I was coming to this workshop, he said, well, maybe you guys can figure out how we can short mathematics. The idea being that AI predicts a future where mathematics will be too cheap to meter. We should have this waterfall of results coming out. So we should enter contracts now for future delivery of this of these results. So I think anyone who can think how to short our subject was probably working in the right direction. So we can talk about this afterwards. On a slightly more serious vein, humans are social animals, but we live in a society where the mystique of the individual is highly developed, and mathematics, writing novels, music, these are areas which traditionally have made a lot out of the great individual contributors, and maybe we have to get over this as a community. It looks like mathematics is destined to become more collaborative, particularly with machines. We may find ourselves more in the role of editors than authors, reading a lot of junk, that's been poured at us, and trying to, find the gems in it, might turn out to be more efficient than digging around in the dirt by ourselves. So those are my initial thoughts. Thanks.
Thanks. Yeah, I also want to talk about the human side of what I am most excited about with the future of AI on mathematics. Kind of about 3 different topics: 1, assistance; 2, mathematical cognition; and then 3, understanding and explanation. And the first, kind of what you were saying, I think that there's a lot of really exciting potential in kind of AI assistance helping people do math better. I think Steve Jobs talked a little while ago about computers being bicycles for the mind. And recently, our kind of metaphors have changed, that now we have these new tools that let us engage with natural language fluently, flexibly, that we've kind of evolved from bikes for the mind to, say, jets that we're kind of working with, to co-pilots. And I think that that shift from tools for thought to sort of partners in thought is really interesting. And I think that some of the work that Jordi and others have done of kind of looking at mathematics, professional mathematicians using AI assistance is really interesting. But I was talking to Mike, what excites me is more on AI for math education. I think that there's a real opportunity to improve the ways that students can learn and find joy in mathematics, whether it's helping teachers to give better hints to students, generate new problems that are personalized to where a student might be having difficulties. I think that's all really exciting that I'd be keen to discuss with folks here. I'm also really interested in mathematical cognition broadly. I think that the power of these new systems to solve math problems that people can do maybe in different ways, maybe kind of failing in ways that people are able to succeed, can give us new ideas and hypotheses that we can test about how we humans are able to learn mathematics, discover new mathematics, and reason more broadly. And I think that's really exciting. And then the third point, kind of related to where people fit in within the space of mathematics going forwards, I think it's interesting to think about what might happen if, say, as we now kind of link up AI systems to formal checkers of, let's say, imagining 20 years, 50 years down the line, that AI systems can now discover a lot of new mathematics, potentially outpacing where humans are able to understand. How can we make sure that kind of humans can kind of keep up in our understanding of mathematics with these new systems? So I think that that's kind of more speculative, but I'd be interested to discuss that with them.
Thank you.
Thanks.
Awesome.
Yeah, let's see, I actually co-wrote a paper in a recent issue of the Bulletin of the Mathematical Society about mathematics and computers. But in that paper, and also the way I'm thinking, I think we need ideally to understand better the mathematical foundations of deep networks in order to understand which kind of mathematics they can help us do beyond the obvious ones like combinatorics. So now, there are a couple of interesting puzzles that I think are interesting. I was looking back at a paper I wrote with Steve Smale many years ago, probably 25 years ago or so. And one of the questions we asked in that paper was, we wrote about learning theory at the time, which was basically support vector machines, kernel machines, and so shallow networks. And one question in the paper is, what about hierarchies? We have hierarchies in the brain, but in the theory of learning we have so far, we don't need real hierarchies beyond 2 layers. So why? So that's one old puzzle. And I think we have an answer now, which is related to compositionality. And Leon mentioned compositionality extensively in his talk. Compositionality is, for instance, according to Chomsky, one of the basic properties of language. It can create infinite type of outputs for a finite number of items. And this is also an answer to another puzzle in neural networks. I think you all know about curse of dimensionality. That's an old story. I think Bellman was the one to mention it, but it's well known that if you have a function of d variables and say the function is it's only C1, so first derivatives bounded, then you may need to approximate it with an error epsilon. You may need a number of parameters that is epsilon to the minus d. Okay? So to put this in context, if your input is a CIFAR images, they are small images, 30 by 30 of dimensionality 1000. Suppose you want an approximation error in the subnorm of 10%, you need 10 to the 1000 parameters. Okay, that's a worst case, but we have 10 to the 80 protons in the universe, so that's a big number. How it comes that neural network can have no problem in dealing with CIFAR or much larger images? Okay, one answer is that if you have a function that is the composition of functions, each one of the constituent function has small number of variables. The composite function may have a very large number of variables. Think of a binary tree. Each node is a function of 2 variables. Okay, so you can make this composite function depending on as many variables as you want if you make the tree deep enough. Okay, for the curse of a dimensionality proof, what counts is not the number of the variables in the composite function, but the number of variables in the constituent functions, so 2. So essentially, functions that are composition of sparse functions don't have the curse of dimensionality and can be approximated without curse of dimensionality by a deep network. It's an existence result. I don't tell you how to learn the net. But this is at the same time, I think, a possible answer for the question, why hierarchies, why deep networks? And the question of why deep networks avoid the curse of dimensionality. It turns out that basically every reasonable function, more precisely, every function that is Turing computable in non-exponential time is compositionally sparse. So it is the composition of sparse functions. Okay, so this is a justification for why deep networks are a good parametric approximator of essentially all practical functions. Okay, you may also say that if you have functions that are not computable, not Turing computable, and there are some. For instance, pseudo-inverse is not Turing computable. You are not guaranteed that you can actually learn and represent this function with neural networks. I'm not sure whether this says too much about whether neural networks will help us to do mathematics. But I think, finding out about the mathematical principle underlying why neural network and transformers and so on work so well will be very important for many, many reasons.
Thank you. Right.
Yeah, so the first point I'd like to make, which is a little bit to kind of take issue with the question, which is, so I feel that there's a kind of a tone of inevitability about a lot of technology. This will happen, this must happen, this will impact you, etc. And if you look at things that have changed our world, like think about a car or an atom bomb or a sewing machine, we've always had a choice of how we react to these things, to some extent. To some extent they're a given, but to some extent we can make choices as a society. So, you think about the atom bomb, this came along and we reacted in a certain way. And I think it's very important to remember as mathematicians that we can choose how we react. And Leon just told me this wonderful story. So his talk was emphasizing stories, and he told me this beautiful story that I'll repeat, and I hope I don't get into trouble. So he said that there was a lot of interest at Meta for developing an AI scientist. And then at some point, the AI scientist suggests that maybe we should develop an AI manager. Okay. And management was not so keen on this idea. And I think it really illustrates the fact that there's a lot of other aspects at play than, how will AI change mathematics, or how might it change mathematics? We have a choice. The second, very broad point that I'd like to make, which is something that, I've had many discussions with people in the audience about this, but I just cannot imagine a world. So I have many of these discussions with mathematicians where they say, everyone always says, imagine we have some machine that gives us proof of the Riemann hypothesis we can't understand. But I find it impossible to imagine the existence of such a machine just in the context of mathematics. If we have a machine that's powerful enough to prove the Riemann hypothesis, we live in a fundamentally different world in which discussions of, will we have a job and things are much, much more broad than just for us mathematicians. I think that's. Yeah.
Okay, so the way I think of it, I don't think a lot at the long term. I'm sort of wondering what happens in usually my mental model is think of just the apparition of computers and how they change mathematics. 100 years ago, mathematicians would calculate this, they would compute decimal system, etc., things that we don't do anymore. When I studied, we were still doing industrial drawing, with rotary and all that, and this was part of the curriculum. We had lessons on how to compute, and this is, in the 80s, it's not even long ago. what I'm saying here is that there's a lot of activities that used to be, staple or necessary knowledge for mathematicians that disappeared because of the computer, but mathematics didn't really change. It's basically the same mathematics as before. I think AI has the exact same effect. I'm really expecting that there will be classes of problems that cease to be problems because, just like finding excellent ways to compute very fast, very long number of decimals ceased to be a problem once we had calculators. Some combinatorial problem, other problems will disappear as interesting problems because we'll have brute force, if you like, machines to do that. So the first thing, I'm really interested in how AI is gonna change the sort of the curriculum or what doing mathematics is about. And I think it goes also the other way, because I think all the discussion about AI is going to raise a number of new questions in mathematics. I was talking about the distribution, this notion of distribution of problems, which is totally irrelevant, I think, from a mathematical point of view, but is central in AI. So I'm pretty sure these new fields are going to appear, or new interesting questions in mathematics are going to appear just because of AI. So I see this evolution more as kind of a pivoting, which is, again, similar to what happened with computer science. So I see that. And then there's a second question, which is maybe a little more long-term, which is, what qualifies as a worthy project, a worthy question, an interesting question in mathematics? And if we have more AI producing ideas or fictions that can be then proven by mathematicians, something like that, it means that there's a number of concepts that we would consider irrelevant or uninteresting, or ways to look at mathematics that are going to change. So I don't think AI will produce different mathematics from the ones we do, but I think mathematics are going to change, and this will be a very interesting things to follow. So this will be my take on this.
All right, thank you. So now we have a second round where you can react or give thoughts or comments.
Yeah, good, thank you. Yeah, I was taken by Gordy's metaphor. You have to decide how to react as to the atomic bomb. I'm old enough to have been trained how to react to the atomic bomb. Get under the desk. Maybe with a little foresight, dig a hole in our backyard and get some plywood to put over it. But perhaps we'll have a more effectual approach to reacting to the developments of AI. I think we need to be good-spirited and going optimistically. Actually, Freeman Dyson was very good-spirited about the development of atomic weapons. He once told me, we should not take them more seriously than they deserve. Which can be read in many ways. But I'm thinking about the sweep of history, and this has happened before. Mathematicians may be somewhat displaced or moved to the side or moved into new roles by AI, but at one point the Titans ruled the world, and the Greek gods locked them up underground so they wouldn't cause any distractions. Well, I hope we don't end up being entombed. But I think we need to be cheerful about our fate and enjoy what we're learning and enjoy our interactions as we go forward, and just get the most out of this very interesting sample of history that we're fated to observe. I don't think many generations will have this exciting life as we do.
Yeah, I completely agree. And I think that also really demands kind of a multidisciplinary approach, which is why it's great that there's this kind of event. So thanks to all the organizers. I think reacting specifically to Francois's point on the kind of move from a calculator and how that might have changed education, at least in my math education, we still had to go for quite a while without a calculator. And I remember in middle school, there was always a debate of whether we'd be allowed to use a graphing calculator or not, when could you, what kind of calculator could you use? And I think these questions will come up in the kind of very near term of what elements of AI systems are allowed to be used in classrooms. I saw there was an interesting professor at Harvard, can't remember his name, but Terry Tao shouted him out kind of on his Mastodon blog of having had students try to prompt a language model to be able to solve math problems and generate new math problems, and that the act of trying to figure out how you would get another system to solve a problem was able to help them learn better, kind of like the Feynman technique, that if you can then teach it to someone else, that helps you understand better. So I think that there's a whole new space of kind of in the near term in terms of joy and optimism to use these systems in creative ways that help us grow ourselves. So, great.
Yeah, continuing on, the thoughts about the mathematics of learning, or the fundamental principle underlying learning, ideally in machines and in our brain, there are fundamental principles. It's interesting that we have very impressive applications, but we don't have a theory that explains why transformers, for instance, are doing as well as they are doing. I think we'll have a theory, and I think it's not the first time it happens. It's actually probably a rule in science. The example I always like to bring is the example of electricity. You mentioned it's exciting this time. Must be exciting when you were in 1800. This was 1800, and electricity up until then was just sparks. And then in Pavia, Alessandro Volta invented the pila, the battery, and it was the first source of continuous electricity. Something like this, disk of copper, zinc, and wood or water, 2.1 volts for about 4 minutes. And after that, a lot of things happened very quickly. The telegraph, the electric motor, electrochemistry, the electrical generators. Remember, he was made a count by Napoleon. Information until then was traveling at the speed of a horse. And almost immediately after that, 10 years later, there was the telegraph. He himself designed a telegraph between Pavia and Milan. And so information went to the speed of light. So things happened very quickly in those decades. But it was many years, nobody understood what electricity really was. There was no theory, despite all this application. It's only really with Maxwell, 1864 or 5, that we had the theory of electromagnetism. And then a lot of other things happened, of course, radio and internet and computers and so on. So I'm sure we are going to get a theory of machine learning. And the big question is whether we will discover the theory, complete the theory, or GPT-10 will do that for us. I don't know the answer.
Yeah, so I'd like to completely agree with Mike's point about optimism. So I think that I actually think it's like very important from a kind of psychological point of view that we maintain a sense of agency. And I genuinely do feel a sense of agency, and it might be an illusion, but I feel like it's very psychologically useful to feel that we can all do something and we can shape our future and things like this. And I do find it absolutely amazing when I wake up some days and I'm just thinking it's so crazy that we're alive right now. And I think it genuinely is absolutely extraordinary time to be alive. I just wanted to follow up on what Thomas said and also Francois. So the motivation for this edition of the bulletin was this really interesting essay written by Akshay Venkatesh on Aleph Zero, which is a kind of math zero system, which I think it reads all Springer textbooks in one night, and then he asks what happens the next day. All the yellow books. And it's a very interesting essay because basically so this ties into Francois's point about the shifting perception of difficulty. So historically, we used to regard with kind of almost awe people that could multiply very large numbers fast. And now we trivialize it because something else can do it that's not us. And so our value system is very dependent on what humans find difficult. And Akshay has this very interesting model for worth in the mathematical sciences, which is basically you attribute worth in a kind of Bayesian way. So let's say that I've never worked seriously on the Riemann hypothesis, but there's other people who have solved problems that I care about who tell me they've worked for 20 years on the Riemann hypothesis. Then I do this kind of update and I'm like, oh, Riemann hypothesis is very hard. And then maybe there's some conjecture that I have very low opinion of. And then someone proves this conjecture implies the Riemann hypothesis. Then I go, oh, I readjust, like I do an update in my mind. And I'd really recommend this essay, but I also found it like very true and helpful in understanding how we kind of sociologically form mathematical value. And yeah, and that really ties into what Francois was saying. And the other thing that I just wanted to say is, I think that there's an incredible possibility in the near term for increased activity in ML theory. Like, it seems like the more that I look at it, and Boris's talk was just extraordinary the other day, like there's just such amazing stuff going on there. And yeah, I feel like that's going to be an incredibly exciting thing for the next kind of 5 years, is to, from a mathematical point of view, understand what's going on in this incredibly rich world, which is neural nets.
Yeah, so you that I've heard make me think of Matt Lewin. I come from the media, so I'm sort of that guy. So Matt Lewin was a Canadian theoretician of mass media, and he mostly wrote about the operation of radio back in the 50s, 60s. He coined the word global village, that's Matt Lewin, which is funny because he coined it not for internet as we think now. And Matt Lewin's opinion on media, his idea on media is very large. He says electric light is a medium. It's mine. It's a medium with no message, but it's a medium. And the point of a medium is that you have something appearing like a communication means, etc. And what the communication means, the message, is not really important. What's really important is how the medium changes your life and lives, and more importantly, how it extends yourself, how it makes you able to do different things. And I think in this regard, AI and the development of AI is exactly a medium. What AI does, the chatbots and all that, ChatGPT, is not really important. What's really important is how we are going to evolve, we are going to be extended by this ability to use AI. And this links a lot with how you train people. This links a lot with what you say about the fact that we still have agencies and we still are free. So there is something very interesting there to see how in life and in science, the operation of these tools are going to change the way we work, but also to make us slightly grow us new kind of senses and way of relating with the world. And I think this is it's a way to be optimistic about the way things are moving.
All right. Thank you for your opinions. Are there any questions, comments?
Said AI is going to make us smarter. If it doesn't, it's not going to exist.
AI is going to make us smarter if it doesn't.
AI is going to make us smarter. If AI doesn't make us smarter, then it's not going to exist because we're not going to be able to do it.
Yes. Yes, I absolutely believe that. I mean, if ChatGPT becomes, the machine that generates the internet, we already have a theory of that as model collapse. It's been studied and people believe it. If you let ChatGPT write Wikipedia, because it's so easy to write Wikipedia and you look right because you update Wikipedia with your ChatGPT, then ChatGPT will be trained on ChatGPT, etc. And the whole thing is going to collapse and it become stupid and we lose and everybody loses. ChatGPT loses too. So it either makes us brighter and then it develops, or it becomes ridiculous and and it doesn't work, and there will be a way. So I totally agree with that.
Can I just ask Leon it sounds very kind of Zen, what you're saying, and so are you saying that like we need intelligence level X to get AI, and we're here, and therefore we must bridge this gap if we want AI, or are you saying something more complicated than that?
I mean, suppose for instance that LLM or big chatbots come like TV, people start listening to them and believe this is the picture of them field. We're going to get so done that we cannot get AI right. And so the only way to produce AI is to become smarter together with the machines. And so yes, there is room.
But also, I mean, there's a very interesting question about equality there also. Like,
Absolutely.
you could have so one person get much smarter and a hell lot of people, other people get lost.
So I get the sort of negative viewpoint of the French education. But I find as being an optimist that I see an opportunity for us to become smarter.
But you would describe it as a co-evolution. It's not the production of AI, it's the co-evolution of humans and AI.
Has to be one of us. It's like for mathematics, when there was a discussion about whether AI could become a better mathematician than mathematicians, it seems silly to me because I don't think that you can do mathematics without humans. Because a lot of mathematics is about communicating to others, exchanging ideas and schemas and so in the very end, it means that the machine can contribute to mathematics and becomes one of us. Again, we go to this notion of co-evolution. We become smarter together with the machines.
Is it permitted for a panelist to ask the audience a question? So Leon, I'm wondering whether an example of what you're thinking of would already be present in Go. Like, are Go masters now smarter because they train on AlphaGo?
Yes. Goes at the chess as well.
Well, chess too, yes.
And but look in the past about writing, the invention of writing. It made us smarter. No question. By communicating more, by exchanging more. So I think there is this kind of effect that advanced is intellectually, physically, we're not smarter than common. We have the same kind of brain, we cannot do more. But in terms of an environment, education, things that happen to us, we're also smarter because we have so much more ability to learn things, so much more ability to do things and to improve. So we need to be smarter. There's no question in that respect, but as a whole, as a society. As individuals, our brain is the same. Hasn't changed.
We're keeping the optimism theme going. I like it.
But I can salute my French side and be pessimistic.
Oh, no.
So I kind of have a question going off of Jordy's first comment and then kind of building on it a little bit. So right now, I think most people agree AI can definitely serve as a tool, right? That seems clear in the near future that it's going to be a very powerful tool. It already is a tool. You saw examples, you saw case studies where it was effective. But I think right now, most people would agree that AI does not provide, or at least in a general sense, does not provide end-to-end information gain, right? You can't put in a set of information and get new information out of it in a way that I think most humans would kind of articulate that idea. And like this kind of leads to the model collapse, right? Humans, well, why didn't we have a model collapse, right? Why didn't humans, kind of all start talking to each other, say stupid stuff, and we all lose our information? We avoid that, right? So we have this insanely complex system, which has been progressively building, right? We haven't had this model collapse. And I kind of feel like most people would articulate that lack of a model collapse in AI as the singularity, right? It's the point at which AI can now kind of build upon itself without collapsing and generate more information. And so do you think we can ever really have like AI, I guess first is, what's your opinion on this like singularity idea? But then also, like, will we ever be able to use AI in mathematical research to kind of generate new information, short of simply having an AI that's able to generally do that?
I think we already have. I'm sorry to quote myself, but the Lyapunov function AI discovers are new things that are discovered by machine. And it goes beyond the training set and all that. So this already exists. So as for the question about the singularity and the model collapse, I agree with you that model collapse is strange. I think Leon has the answer, or basically the general idea of the answer. It's around fiction that it happens. I mean, we are inventing new things because we think all the time and we play games where things are not really true, and we invent things that means nothing, and we have no problem cheating and not playing by the rules and saying if this weren't true, etc. And you do that all the time in math. I mean, you have a definition that doesn't work well, you change the definition, you adjust a special case, etc. You modify the rules. I think machines are not able to do that these days because of the way we do it, because probably of the way we sort of revert them and want them to be true, and we're very obsessed by that. We want the LLM to be correct. We want the LLM to be right. We want to correct that. If we treat them as fiction machine, which produce fiction, which can be right, which can be wrong, etc., then it changes. So I think the model collapse comes mostly from this tendency we have that we want to have machine that say the truth, act correctly, are responsible, do what we expect good machines should do, etc. And we're putting kind of a straitjacket around them. And that would be my interpretation of the current problem.
That's interesting because I feel like a lot of people would articulate kind of the opposite perspective, right? Which is that they're really good at generating fiction. In fact, that's all they're good at. They can't generate truth, right? As much as you try to make them generate things, they don't have this discerning ability, right? You can play around with a ton of mathematical ideas like string theory, but when you look, we can somehow check this against reality, right? We have this ability to be discerning about theories and things we come up with, right? So when we come up with GR, we can now have high confidence in it, right? We did Eddington experiments, we see these results, and we can confirm this. We build up confidence in things in a kind of structural and like cohesive way. Like AI, I kind of feel like a lot of people are can't really do that right now. It has a discerning capability, it hallucinates and happily parrots things, and it can't quite. It can make things up as much as it wants, but it can't actually figure out then what to latch onto and decide is correct.
So maybe two comments. So the first one is that I think it's like an interesting experiment to imagine like you talking to someone else with no real world for 40 years and to see if you experience model collapse. And I kind of think it might happen. And so I don't know, my instinct as a total novice, at the theory of these things is that somehow the groundedness in the real world is extremely important. That, exactly as you say, we can do experiments, we can touch things, we can throw things. And one of the things that I think is very interesting at the moment is that you're starting, when ChatGPT came along, people, I think everybody who I spoke to who was somewhat aware of kind of RL and generative models was like, oh, we just have to hook this up to some kind of evaluator. And, and I think that it's interesting that there's kind of basic technical difficulties in doing so. So people tried to do so, and it's really, like one basic thing is that LLMs love like batch sampling, and that somehow plays very, very poorly with RL systems. But now we're starting to see it. Like alpha proof, for example, is a situation in which you're generating, billions of proofs. Most of them are crap, but then some of them are working. And so you do have that groundedness in some kind of reality. And yeah, who knows where that goes, but.
I would like to add that groundedness and the idea that, especially scientists, scientific method and all that, we're always a bit exaggerating on it. Because not everything we say is grounded in practice, and even science. We've got parts of science with experiments that don't work, that don't act the way they were supposed to go, and we live by it. And we have counterexamples of stuff, and we have theories that are slightly contradictory. I won't name names, but there are tons of those, and we still manage. So when you say, oh, we have this experimental method and a single fact, and we change the theory. No, we don't do that. So we're sort of holding machines at standards we don't have for ourselves in this area. So yeah, I think part of the problem is, the way we believe we are very logical and serious, etc. The way we believe truth and we judge it by our own standards. Whereas we probably exaggerates, all logical character and the illogical character of the machine. If you look at ChatGPT's hallucination are not that common. You need to look for them to get them.
That is my experience.
And I think also adding one other thing, I do think that in the very near term, the kind of link between informal and formal mathematics of having systems that can generate, say, lean, and then also go back and kind of generate back to natural language, which Albert Zhang at Cambridge and some others like Pei Yang at Caltech have been doing really good work in. So I think that's an interesting direction of one element of groundedness in some way, but different from the kind of groundedness that humans experience.
Yeah, I'd like to get into the question of AI as an intelligence amplifier and grant that we have, against a much higher level, which we won't specify. And now I'd like to ask, suppose, I'm, trained as a physicist, I know some mathematics, but now I get interested, or somebody gets interested in the language program, something very far from my training. And of course, as things stand, it's very difficult. You need like experts, it's this vast amount to learn to do anything. And I might imagine in some future that, well, here's this conceptual framework, which indeed takes hours to learn. But given that incredibly high level conceptual framework and my AI assistant, I can actually do things and read papers and understand and conceivably contribute. And is that a conceivable dream, or is it that mathematics is sufficiently irreducibly complex that, well, it's true that it's still going to take you a year to really understand what's going on? What would you mean?
I think a very important ingredient to this assistant you're talking about would be a lot of detailed knowledge of your previous work. Because, if someone who really understands the subject, you ask them a question and they know you, they can answer the question to you particularly. And you don't have to read all those papers in detail, perhaps.
Right. So that's right. So it's interactive. It can talk something about it.
Right. They'll find like the best match between string theory and the language program and explain it to you that way.
But then you might be taking either position, because you might say, well, yes, language turns out to have similarities with string theory, and that's the part that you will understand and not the rest, and somebody else will get some different point of view. Or you might take the position that says, well, yes, there is this high level summary, and once you understand it, whoever you are, now you can work with the language program.
That'll be a lot deeper and longer summary, I think, if it's general.
But you don't think such a short summary could?
Well, I just think, you have to build on what you're comfortable with, starting somewhere, I mean, you might, now, of course, you might imagine this personalized textbook being written for you in real time, and you can click on any concept that you don't really understand. So if you're weak on differentiation and you're reading a physics textbook, you just click on this, and the formulas that were obvious to the better trained reader now are made explicit to you, and after that happens a few times.
Yeah, that's right. We're imagining the tools are as good as we can, better than we can imagine. But now is there kind of this reducible structure and complexity that just you have to live with it and study it.
Well, I can't imagine the barrier can be lowered indefinitely. I think that there. I mean, but then of course there'd be creativity on the AI's side.
Yeah.
That every year the AIs will be talking to each other and saying, how can we make Mike Douglas just a little bit smarter than he is? He looks promising, if we could just get him over this.
Just a comment on that is that I literally do this like every week. So, because I've been experimenting, like essentially because of work in machine learning, I suddenly need to know a whole lot of applied math and machine learning concepts. And something like, a couple of weeks ago, I needed to know what a Gaussian mixture model was and how the algorithm works that fits it. And, I spent about an hour and a half talking to ChatGPT saying, what's the Gaussian mixture? And then it starts explaining and I say, oh no, I understand that. Can you explain that bit or something? And, I think that the speed at which one can learn in that way is so much faster than if I take a textbook that's guaranteed to either be like assume that I know too much or assume that I know too little. And a lot of stuff in machine learning, I just, I chat to my llama on my phone about, how do I think about Adam? How is Adam different to SGD or whatever? And my rule is that if like 2,000 people on Earth know it well, then probably it's going to be learnable in this way. But if it's something that 3 people know, then no chance. You can totally imagine that getting somewhere near the level of, specialized knowledge within a short order of time.
I do think it is also interesting of how fast humans can learn. So I don't think that we're going to be able to get to kind of infinite, just rapidly having people learn as fast as possible. I think that gets to Leon's point about kind of hopefully humans can keep getting smarter, but I think there'll be a limit to what our learning rate is for any given problem.
Just a kind of maybe a negative comment on tools that violate my optimism rule. When I watched Thurston and Sullivan developing a theory of rational dynamics, in Thurston's case, using dynamics like the skinny map in order to solve the geometrization problem. This was all before these beautiful coffee table books came out, where you could see the Julia sets and all that sort of thing. So like the ability to visualize complex sense of complex numbers, complex dynamics actually came later. In my view, it'd be great to have a real expert like Gordon McMullen in the room to have him comment, because he probably knows the work of some younger people that would perhaps contradict what I'm saying. But from my impression, the great discoveries like the wandering domain theorem were done before the pictures were made. People thought about it in a way they were able to see what they needed to see. And it wasn't like the full color drawings, but math somehow has succeeded in pushing forward without explicit renderings of visualizing data that's been seen in science, and with our very limited abilities to formulate a high dimensional model in our brain, we've done amazingly well in the past.
I have a question pertaining a little bit to like mathematics and education, especially. I've been thinking about like we were describing AI as potentially creating fiction, but then needing an evaluation machine afterwards. Do you think there's a space in which the teaching of mathematics should be focused, or at least spend time on helping students discern what the wrong answers are, and instead of focusing on can you get the correct answer, can you tell me which of these options look wrong? Maybe similarly with higher mathematics, maybe it's not about getting the correct proof, maybe it's saying, okay, this proof is incorrect, and let's see.
I do think that's a great idea as a teaching technique to help kind of students know how to discern and sift through. And that seems like a very important part of AI literacy broadly, not just in mathematics, but other areas that we might have these tools kind of helping teach us in different ways. I think it's a good idea.
I definitely know people that have posed those kind of questions on, like for their students, get ChatGPT to give you a proof of this and like explain why it's either right or wrong.
Especially if the statement you ask it to prove is false.
Yeah.
Yeah, I mean, there are parts of, sorry, just one comment and then you can ask. But there are these setups where essentially you have some reinforcement learning agent where you sort of have some statement you want to prove, and then it will suggest sort of different theorems you can apply to the statement. And if you sort of just do something like a beam search, or so you just sort of say, okay, so there are the machine things sort of applying this theorem or rephrasing it in this way might be helpful. And then sort of a human might interact with this machine by looking at it and say, okay, so pick what applies. So it's a group theory problem, and they want to apply something from some completely different mathematical domain. Maybe that's not the way to go, but here's a proposal of sort of rephrasing it as a different problem in group theory. So.
But the beam search only works because you have a machine that does the verification. I mean, suppose every time you ask a question to ChatGPT, you give a 10 answer and 9 of them are wrong. You won't like ChatGPT for minutes. I mean, your role is not to, to receive from ChatGPT a lot of answers. 1 or 2 of them are right, and you're supposed to find the wrong ones. If you want AI to be, yeah, maybe to
fine tune the models.
that's not right. I mean, obviously you cannot. I think you want to train students to be able to discern what is wrong, etc. But you cannot put it. You have to have the machine produce globally correct things, or it doesn't become a tool. Not supposed to.
Yeah, I agree. But I think sort of this is part of maybe if you include this in early education of working with the machine in this way, there's a way of interacting with it and teaching some students from a young age to sort of interact with it in this way.
Yeah, I think so.
This might be something sort of which probably in the near future, how the interaction between a mathematician and these systems will conceivably be very useful.
Yeah, so both Francois and Jordi with the idea of agency, that we don't have to allow AI math system to sort of change society, or we don't have to go down that road. And that got me thinking, under what conditions might you want to put the brakes on this? In a sense, I guess I'm asking, what are the possible dangers or risks in developing AI mathematics systems? Are we engaged in an entirely benign endeavor here?
I mean, I think it's an excellent question, and I guess the point that I made at the very beginning is we should be asking ourselves this question, and it's very important to ask this question. Sorry, we keep dodging it. And to be honest, I don't know. And I don't think that any of us know. There's a very recent meeting in Seoul of many experts in AI, and they produced a very interesting document about risks associated with generative AI, and there's some discussion of how likely certain risks are to eventuate, and what one can possibly do to mediate such risks. And I think it's a fascinating document, and I think it's a very balanced document. One of the very interesting things about the document is that there's no involvement of anyone that's associated with a big AI lab, which I think is a very good stance. We should be asking ourselves this question. We should be discussing this. Before ChatGPT, I was trying to get people to talk about AI, and it was just so frustrating for me. I felt that there's really something happening, and no one is really talking about it. No one really cares. People care about what the weather's going to be on Sunday. It's a bit, yeah. So I'm very glad we're having this discussion. Summary.
I think there are ways you can already, make choices. For instance, you write papers. When you write a paper, how much do you want to use ChatGPT to write parts of the paper? Do you want ChatGPT to write your introduction for you? You review a paper and you're bored about this paper. Do you really want to read the paper, or let ChatGPT provide you with with a bad version or with a bad summary of the paper, and you save time? So we already have agency in how we want to use those tools in scientific practice. You review a paper that is obviously written by ChatGPT. What do you do? So I think we can make choices now on this, and it's always individual decision, but it's like the automatic manager or the automatic scientist. Do we really want an automatic scientist that write beautiful texts that are full of nothing? No, we don't. And that's
But these decisions that you're speaking of are on individual level.
Yes.
And I don't think there's any mechanism to make societal decisions. If there are hazards that we should be worrying about, I think we're out of luck, because the world is a big place.
I totally disagree with that.
We're not all going to get together and decide to avoid certain dangers. Some people are going to push forward.
I mean, we, in theory, we live in a democracy and we can.
Well, who was we? That's true right now. But
Stop me. Getting your point.
sorry,
How are you going to stop me?
you.
Yeah.
Yeah, I know, I only have so many cudgels. But yeah, I mean,
That it's gonna be very hard to control the developers.
I think it's following some kind of differential equation and we don't know the coefficients, you know? We're not gonna, by our agency, change the equation. We're gonna watch it unfold.
Yeah, I sort of disagree because I believe, the AI community has a say on AI. We cannot say, oh, we're so many of us, we don't have agency. No, we have agency. We are the people who work in AI. So I can understand that many people can say, I can't help it.
But it's a big world. I mean, the community you're speaking of, does it include Chinese scholars?
Yes, it includes Chinese scholars, and I think they have some of them has the same question as we have. And I sort of have faith in human nature on that. I believe people have the same problem everywhere, saying, if you let all the scientific content be written by machine that just write nice work, we are in trouble.
But scientific enthusiasm is notoriously irrepressible, even when there are dangers. If I could mention one other story from Freeman Dyson, he told me that at the end of the Manhattan Project, when the Truman administration was pressuring the scientists to stay together and work on the H-bomb, that the sentiment was about 70-30 against it. The consensus was there was no reason, no possible justification for doing this. And then a technical innovation, Teller, Ulam, and Garwin came up with this neutron reflector idea. He said once this idea was explained in seminar, it was so fascinating that it switched from 70-30 to 30-70. They wanted to see if it worked. And well, if that's the end of humanity.
At least we'll know.
That happens. I mean, it really impressed me, that story. I was just a mathematician and I hadn't dipped my toe into physics. And it really impressed me about physicists that they were so fascinated by their subject that the possibility of ending the world was just one of several constraints.
Maybe just on that, so there's a fascinating article by George Orwell called You and the Atom Bomb. And it was written, I think, around about 1946 after the Second World War. And basically his first paragraph is that there's been lots of articles which tell us in great, these schematic diagrams about atom bombs. I don't care about any of that. What I care about are how easy are these things to make. And he basically says that if something is in the remit of governments, it's going to be a tool for suppression. But if anybody can build it, then there's going to be a kind of natural equality that's going to emerge. I have no idea if this is correct or not, but I think it's very interesting in the kind of to your question about what about me, I feel like if the ideas are out there and there's a whole lot of me's, there's not as much danger as if the only people that can build these things are gigantic labs and they're out of control.
There are self-limiting moves. Like, for instance, I have a very smart colleague who took the habit of reading papers by first sending them to GPT and read a summary to get an idea. And it came to me and said, can I believe this paper? It says that. Who wrote it? Shabelkin, Serious Gabi. Yes, but it says it. Can I believe it? I told him, well, if you read the paper yourself, you would know. And so it's a self-limiting move sometimes. So sometimes you want to read the paper yourself.
So I'm a physicist, I'm not a mathematician. Partly it's because math is hard. And maybe because it's easier in a way. But there's different levels of hardness. And I find that there's some math that I think I could do if I work very hard on it. And some math that may be beyond me. you know, and there's a spectrum, there's a scope, and I imagine for everyone, there's sort of some limits to the kinds of questions we think we might be able to answer, and there's all our own personal motivation. And I know, you know, like the proof of Fermat's theorem, maybe if I spend 10 years, I could understand, I really devote myself, I don't know what the scope is, maybe 10, maybe 3, maybe 30. But if you think about the scope of problems in math, there's some time scale for any individual that might be able to, you know, understand it and make progress, and that changes with time, and it changes with the individual. Right, and you can think about, you know, our species, the kind of problems that we're able to solve in a finite amount of time, maybe 100 years, right? And that changes with time. If you think about the type of problems that, you know, the Neanderthals could solve, they were much lower just because of the brain capacity. I mean, there's things that change with evolution, and then there's things that change with society. But there's certainly a range, and then you can think more broadly about the questions in mathematics that are solvable at all, right? And then you can look at that, and that may be infinite. Right? And so in that infinite space of solvable math problems, there's some finite volume that human beings might be able to solve in a finite amount of time. So you can imagine that, you know, eventually, if we keep evolving, we'll get a broader and broader amount of those problems, right? But we'll never get all of it. And machines can help us, and maybe they'll expand the sphere of problems that are solvable and understandable by humans. But it certainly seems reasonable to me that, you know, even if we can enhance our intelligence to get a bigger sphere, we're not going to get that much bigger, maybe a factor of 2 in some measure, but if you keep letting the machines evolve and get better and better, and maybe there's some notion of a singularity or something, they don't have the same kind of mental limitations that we do that prevent them from getting bigger and bigger and arbitrarily larger. And maybe they could try to, some of those, you know, when they're understanding problems that are twice as hard as the ones we're studying, they could explain it to us. You know, and dumb it down and write a popular science book that we can interpret and you know, give us some sense of what's going into this. Or maybe, you know, explain it in such a way that we could now understand it in 10 years instead of 30 years. But it seems to me that asymptotically, there's a large swath of math problems that machines are going to be able to understand that we're not, and some scope of it that we're going to be able to understand and some we aren't. So I mean, just hearing from you, it seems like, oh, math is really about people and understanding things, but it seems to me that if you just take a step back and think of us on the spectrum of intelligence, we're just a little blip, and math doesn't care about humans. So why should the interesting problems in the intersection of what human beings can do in 2024 have any relevance? I'm curious why you're so human focused.
Well, I think we supply the background measure, you know, well, because that's our choice, that's our agency, we decide what's interesting. You know, what's derivable from the axioms, that's out of our control, that's like some pre-existing thing, once you fix the axioms. But which are interesting theorems to us.
Interesting things, right? I mean, you could say, the scope of interesting problems, there's also an infinite number of those, not all of those will be able to understand.
No, sure, there are things we would never be able to understand that if we're a little broader, we might be able to, but one of the things I think we might expect from collaboration with artificial intelligence is some kind of meta understanding of the way mathematics looks. Like, to make an analogy again with these like coffee table books that Julia sets, you know, I imagine, you know, that the page is all possible statements or something, and then there's this beautiful swirling pattern of theorems, you know. What does it look like? You know, what's the structure of mathematical truth? I mean, it seems like it's pretty fractal in nature, otherwise you should be able to figure out an algorithm to go to directly to the theorem, you know, proceed from one fact to another. So mathematics, you know, has some internal structure, which probably we've explored so little of it that working mathematicians today might not have much intuition about what math looks like, but maybe when machines can check billions of possible theorems, they can communicate some overall geography of mathematics to us that's way beyond us.
And I agree. I think it's also interesting of then how, if we can characterize what that space of mathematics is that humans can understand, can help us better understand humans in the first place. So I completely agree with you that it's possible, if not very, very probable, there is a vast space of mathematics that we won't be able to understand. I'd be curious what you think if we should even be building those systems that can search that space of mathematics beyond what humans would be able to understand, or say if a machine was able to discover some part of mathematics that we could have checked that it's kind of, or we know it's correct through, say, some verifier that's giving you a response that is correct. but that there's no way to map from what the machine has done to some kind of human understandable proof. Would that be something that would you find upsetting or think that we should avoid building systems in that direction?
Like one thing that I very strongly believe is that the statement that mathematicians want to prove theorems is false. And I feel like it's very important. So, you know, a mathematician is a machine that turns copy into theorems. Okay, this is the definition of a mathematician. And I think it's a wrong definition of a mathematician. And I think it's like, there's an amazing article of Thurston called On Proof and Progress in Mathematics that discusses this question in great detail. And so, you know, you're imagining a situation in which somehow machines can explore this enormous swath of mathematics that we can never even comprehend. But that situation already exists. There's many, many theorems that are proven on computer, you know, for example, this Pythagorean triple conjecture, that we can never hope to fathom. But we associate much less meaning to that than the proof of Fermat's last theorem. And so I think that it's important to remember that mathematics is a human activity.
But don't you think that there's a notion of elegant proof? You know, not just, you know, an enormous case analysis. A proof other than enormous case analysis that's really getting at something fundamental. And the machines, even if you restrict, you know, talk about the subset of mathematics that's has that structural property, it could still go way beyond what we can understand.
Yeah, and I think that if we could get meaning from that, then that would be incredibly valuable for us.
Yeah, there is a paper by Gower about the manifesto about the old set of theorems for which you can have the statement and whether there is a proof and or not. And this set is B for boring. And then a subset of it is M, and this is what mathematicians can actually understand and are interested in. And the question is poses is, what is M? Why is feasible for mathematicians to prove and understand that subset and not the other one? It's a paper, 50 pages.
I wonder which part of it.
Let me add the comment that there's mathematics of means or tool, there's mathematics of an end. And a lot of the discussion has been mathematics as an end, you know, where the end is understanding and human benefit. And of course, if you're using it to solve some other problem, then it's much more important to solve the problem, you know, if you don't understand it. And then maybe a good example in the present technology is the protein folding problem. We have a beautiful theory that helps us understand the structure of proteins and how they fold. On the other hand, we have AlphaFold 3 that really gives us these very effective answers, even if it's very complicated and messy and hard to kind of understand. And they're both valuable, but you know, certainly if you're the biologist wanting to work with protein. But many of these results, you know, there's this large sphere is going to be in that category. It's just people. If it's an abstract, beautiful result, well, then we don't understand it. It's just sort of interesting, but if it's something we need, obviously, we're very interested.
But you're defining, looking at mathematics, interesting to humans, that humans like, then sure.
There's these two sources of interest.
Yeah, but then machines obviously aren't going to achieve superhuman abilities and things that humans, the definition is things that humans can do. I mean,
Well, no, but
there's no domain of superhuman. So in the other.
Well, no, I mean, there could be also a proof of the Riemann hypothesis. This, you know, thing that is, yeah, been said many times, 200 terabytes long, you know. You know, it's something, you know.
So you don't give any credit, the machine understands it, that's not valuable? It has to be a human.
We have to, well, no, we even now we have to talk about what does it even mean for the machine to understand it, getting into the previous discussion.
Well, I don't think it's any different from me saying, what does it mean if you understand it, and I don't.
It's different. We can talk about it.
There's also a human element in mathematics and just saying what the definitions and the axioms are from which you're going to derive the rest of it. and just conceptualizing, whether it be from the natural world, or the human world, biological world, maybe the machine world eventually. What is mathematics, right? There's a big human element that goes into that. Now, maybe machines will invent a new mathematics.
Maybe you end up with a situation, maybe in the, I don't know, but in the 17th or 18th century or 19th century, you could publish a theorem that say this 77th decimal is this, it's pi of this, I calculated, and this would be a theorem. This would not be a theorem anymore. It's just running a machine, it's just a calculation. So maybe tomorrow, if computers can brute force things, the status of those discoveries will be different. Like calculation used to be theorem, not just calculation. So maybe something like that is going to happen when machines are able to brute force things.
Maybe there'll be some distinction between various ways of knowing mathematical facts that will emerge with machines that might be human understandable arguments that can't be made completely rigorous. I remember mathematical physicist Sergei Novikov gave some lectures at Harvard where he began that the fraction of mathematical facts that physicists know and mathematicians can prove is very small and converging rapidly to zero. So, one thing I've appreciated with my interaction with condensed matter physicists is, through numerical simulation and models and renormalization and scaling arguments, we can become certain of some facts, statistical physics, for example, as you are with mathematical proofs, but there are no proofs of these things, and probably they may be incomplete or something. There may not be short proofs. So, going back to like this Thurston essay, there was an interesting rejoinder to that essay written, slightly bitter tone by Frank Quinn.
No, it's Thurston was a rejoinder to to Quinn and Jaffe.
But I remember in the Quinn Jaffe article, not only were they critical of Thurston for alleged carelessness, which I don't agree with, but they were critical of Poincaré for steadfastly refusing to say what he meant by manifold. And depending on context, he would either use the infinity overlaps, topological manifold, or triangulations, and different kinds of triangulations. And it seemed to be a point of pride with him that he wouldn't say, because he wanted to use different techniques in different contexts. And so it may be that we would have some haphazard understanding accessible to us of the Riemann hypothesis, but it might be terabytes of proof if it's written out in formal language. And that actually might convince us that there are other ways of knowing things than plowing through these terabytes, that we might look at other disciplines like condensed matter physics and say, gee, they seem to be pretty certain of their facts. Maybe we incorporate that.
Yeah, on that note, I think we have to conclude the discussion here. So let's thank the panelists. And thanks to all of you for participating and asking these interesting questions. We conclude here, but of course we have this program going on for 2 months. So different people will or will not be around, but I hope, of course, there will be interesting discussion continuing on the subject. So thank you very much.
Thank you. Thank the organizers.